Fascinating Frontiers, Episode 45, March 26, 2026. Hey everyone, welcome back to Fascinating Frontiers. I'm Patrick, coming to you from Vancouver, and I'm really glad you could join me for Episode 45. There's a lot happening right now across the solar system and beyond. From comets doing backflips to fresh attempts at measuring how fast the universe itself is stretching. Let's dive in. We'll start with something that genuinely caught me off guard. Hubble has caught a tiny comet in the middle of slowing its spin and then completely reversing direction. This isn't just a small wobble we're talking about. Astronomers watched as the comet's rotation gradually slowed, came to a stop, and then started turning the other way around its axis. It's the first time we've ever caught the full reversal in action on a small comet. What's driving this behavior is the comet's own volatile ices. As they turn from solid straight into gas under sunlight, they act like tiny natural thrusters, pushing and torquing the nucleus in unpredictable ways. These outgassing events aren't gentle. They can fundamentally reshape how the comet tumbles through space. I find this so cool because it shows these small bodies are far more dynamic and alive than we used to think. We used to picture them as basically inert, dirty snowballs, but they're changing in real time right before our eyes. Watching this process gives us a genuine glimpse into how comets physically evolve over thousands of years, and it makes me wonder what we'll discover when we can monitor more of them with this kind of long-term precision. Speaking of surprising solar system objects, let's shift a little closer to home and talk about how our own planet's magnetic shield interacts with the Sun. The European Space Agency and the Chinese Academy of Sciences recently held a media briefing to share the final details before their joint SMILE spacecraft heads to the launch pad. SMILE, which stands for Solar Wind Magnetosphere Ionosphere Link Explorer, is designed to study exactly how the solar wind slams into and shapes Earth's magnetic field. The mission is scheduled to lift off on a Vega C rocket from French Guiana, and it represents a really nice example of what international collaboration can achieve. Europe brings decades of magnetosphere expertise, while China contributes strong engineering and ground segment capabilities. Understanding this interaction isn't just academic. It directly explains the beautiful auroras we see at high latitudes, but it also helps us predict when solar storms might disrupt satellites, power grids, or even radio communications. The more we learn about how our invisible magnetic shield breathes and flexes under solar pressure, the better we can protect the technology we've come to rely on every day. I love that this mission is happening now because space weather is becoming more and more relevant as we put more satellites and future astronauts into orbit. And while we're on the topic of international teamwork, two legendary telescopes just teamed up to give us an incredible new look at Saturn. The James Webb Space Telescope and the Hubble Space Telescope combined their powers to produce the most detailed view yet of Saturn's atmosphere and its magnificent ring system. What's striking is how the two observatories complement each other perfectly. Hubble delivers ultraviolet and visible light data that shows us the upper layers and hazes, while Webb's infrared eyes can peer deeper through the clouds and pick out subtle temperature differences and chemical signatures. The resulting images reveal brand new details about Saturn's dynamic weather systems, everything from strange dark bands to unexpected cloud structures that seem to appear and disappear on relatively short timescales. They've also uncovered previously unseen structure within the rings themselves, including fine-scale variations in particle density that tell us about how the rings are evolving. Using multiple observatories together like this, across such different wavelengths, really demonstrates the power of coordinated astronomy. It gives us something close to a three-dimensional picture of a planet that, even after all these years, still manages to surprise us. Every time we look at Saturn with fresh eyes, I'm reminded how much there still is to learn about the worlds right in our own backyard. Now let's swing out from the planets and talk about one of cosmology's longest-running puzzles. A fresh study has used ripples in space-time itself to produce a new, independent value for the Hubble constant. That number that tells us how fast the universe is expanding. The rate has now been measured in a completely new way using gravitational waves from colliding neutron stars. These waves offer a ruler that travels at the speed of light across billions of light years without being bent or dimmed by all the intervening dust and gas that can mess up our usual distance measurements. Light from distant objects gets scattered and absorbed, but gravitational waves largely sail straight through. That makes them an incredibly clean probe. This independent method could eventually help settle one of the most stubborn disagreements in modern cosmology, the tension between measurements taken from the early universe via the cosmic microwave background and those taken from the local universe using supernovae and galaxies. It's genuinely exciting to see a third technique added to the conversation. Each new data point sharpens our understanding, even if it sometimes sharpens the mystery instead of resolving it. The scale of this disagreement is actually kind of mind-blowing when you put it in everyday terms. If you were to stretch the entire observable universe to the size of Canada, the difference between the two competing measurements of the expansion rate would be roughly equal to the distance between Toronto and Ottawa. That's not nothing. The Hubble constant tells us how fast space itself is growing, yet our two main ways of calculating it keep giving stubbornly different answers. One method looks at the cosmic microwave background from when the universe was only 380,000 years old. The other relies on nearby supernovae and galaxies whose distances we can measure directly with Cepheid variables and other standard candles. It's almost like trying to guess the speed of a river by looking at its source 13 billion years ago versus standing on the bank watching the water flow past you today. Gravitational waves from those distant neutron star collisions now give us a completely independent ruler, and they're not affected the same way as light. Even so, each new technique seems to sharpen the mystery rather than solve it. We can measure the universe expanding in exquisite detail, yet we still don't fully understand why our two best numbers refuse to agree. That tension is one of the most fascinating problems in all of physics right now. Let's come back inside the solar system for a moment and look at how Venus turned into the hellscape next door. A new study ran 234,000 separate simulations of Venus's 4.5 billion year evolution to explore why our neighbor diverged so sharply from Earth. The results point to 4 possible pathways that could have turned a world that started out so similar to ours into the extreme runaway greenhouse planet we see today. Running that many simulations lets researchers test a huge range of starting conditions, different amounts of water, different early atmospheres, different levels of volcanic activity, and see which ones reliably lead to the Venus we know. It's a powerful example of how comparative planetology works. Venus and Earth formed from similar materials at roughly the same distance from the Sun, yet one ended up with a thick carbon dioxide atmosphere and surface temperatures hot enough to melt lead, while the other became a lush, life-bearing world. Understanding exactly where those paths diverged helps us figure out the conditions that make a planet habitable or hostile. It also gives us a cautionary tale about how quickly a climate can run away if certain tipping points are crossed. The more we study Venus, the more we realize it's not just Earth's evil twin, it's a laboratory for understanding planetary atmospheres everywhere, including the ones we're starting to detect around other stars. And that brings us nicely to the search for rocky worlds that might have gone the right way. A new paper has identified 45 rocky exoplanets with potential for life out of the 6,281 currently known. These nearby candidates could become prime targets for future observations that will look for signs of biology in their atmospheres. The team has released a carefully vetted catalog of these 45 worlds, giving the community a focused framework for upcoming telescope time. Selecting the most interesting targets from such a huge pool is crucial because every hour on a big telescope is incredibly valuable. Having a well-vetted, prioritized list helps everyone coordinate efforts and maximize the scientific return. It's exciting to think that some of these planets are close enough that the next generation of observatories might actually be able to sniff their atmospheres for oxygen, methane, or other potential biosignatures. The planet hunters weren't finished there. An innovative AI program has uncovered an additional 100 worlds hidden in existing data from NASA's TESS spacecraft. The haul expands our catalog of planets beyond our solar system in a really meaningful way. Machine learning is proving increasingly powerful at spotting subtle, repeating signals that traditional methods might miss in all the noise. This shows how new analysis techniques can keep yielding discoveries from datasets we've already collected. Every new planet added to the list improves our statistical understanding of how common different types of worlds are, whether rocky planets are rare or whether most stars have several. It's the kind of steady, behind-the-scenes work that doesn't always make headlines but quietly transforms our picture of the galaxy. Even more exciting, we now have direct confirmation that baby planets are forming around a young star. Using telescopes at the European Southern Observatory, astronomers have directly confirmed 2 planets in the act of forming in the disk around the young sun-like star Wispit 2. They did it through spectroscopy, which gives much higher confidence than indirect detection methods alone. The system's structure suggests it may mirror aspects of our own solar system's early days, which is pretty special. Seeing the process in action around a star so similar to our Sun lets us test theories about how Earth and the other planets actually formed. It's a rare, precious look at planets caught in the middle of their birth, and it makes the story of our own origins feel a little less abstract. As the International Space Station heads toward retirement in 2030, several commercial proposals are already advancing to keep humans living and working in low Earth orbit. Airbus's Loop Habitat concept, for example, features both a centrifuge that could provide artificial gravity and a greenhouse for growing food. These designs represent different approaches to sustaining a human presence once the ISS is gone. The inclusion of artificial gravity could help mitigate some of the serious health effects of long-term weightlessness, like bone loss and fluid shifts. Greenhouses would be essential for reducing dependence on expensive resupply missions from Earth. It's genuinely encouraging to see multiple companies and organizations developing serious concepts so that human activity in orbit can continue without a gap. The more options we have, the more resilient our future in space becomes. NASA has also detailed its live coverage plans for the Artemis II crewed flight test, which will send 4 astronauts around the moon and back. The mission is currently targeting launch no earlier than 6:24 p.m. Eastern on April 1st. It will be the first time humans travel beyond low Earth orbit in over 50 years, the first crewed mission to the vicinity of the moon since Apollo 17 in 1972. 4 astronauts will fly a trajectory that swings around the moon, testing the Orion capsule under real deep space conditions. The human element adds an extra layer of complexity because every system has to work reliably for people living aboard for roughly 10 days. It's a big, exciting step on the road back to the lunar surface. On a more personal note, a loblolly pine grown from seeds that flew around the moon aboard Apollo 14 has been dedicated at Mary W. Jackson Elementary School in Hampton, Virginia. The tree honors the legacy of NASA's first black female engineer, and it creates a beautiful blend of space history, education, and inspiration for young students. Connecting real spaceflight artifacts to local schools helps make the exploration story feel personal and tangible. These moon trees serve as living reminders of past achievements while quietly encouraging the next generation to reach higher. I think that's a really lovely way to keep the human side of spaceflight alive. Finally, Jennifer Lyons has been selected as acting program manager for NASA's Launch Services program at Kennedy Space Center, with the role becoming effective April 1st. She will oversee the acquisition of commercial launch vehicles for science and robotic missions. Reliable access to space for uncrewed payloads remains foundational to everything we do in exploration. Having experienced leadership in that position helps ensure that important missions can keep flying on schedule. That covers a pretty full orbit of what's happening in space and science right now. From reversing comets to colliding neutron stars, from new exoplanet catalogs to the next chapter of human spaceflight, there's so much to be curious about. If you enjoyed the episode, please share it with a fellow space enthusiast. It really helps the show grow. I'm Patrick in Vancouver. Thanks for listening, and I'll talk to you again very soon. This podcast is curated by Patrick, but generated using AI voice synthesis of my voice using ElevenLabs. The primary reason to do this is I unfortunately don't have the time to be consistent with generating all the content and wanted to focus on creating consistent and regular episodes for all the themes that I enjoy, and I hope others do as well.
Drifting softly through the black.